Okay, we're looking at 10 for slope in polar form. Okay, so given the differentiable function r equals f of theta. So remember when we were doing our conversions between rectangular and polar, x was equal to r times the cosine of theta, and y was equal to r times the sine of theta. So if we think about the slope in polar, if we want dy dx, then we're going to define this polar curve parametrically. So x equals r cosine theta. What's r equal to? R is our given function, so f of theta times the cosine of theta. Y is equal to r sine of theta, so replacing r with our given function, f of theta times the sine of theta. Okay, so now that we have our parametric equations in terms of theta, now we can derive each one. So look at each of these, x and y. The derivative will take the product rule. So the derivative of y with respect to theta, first times the derivative of the second, plus the second function times the derivative of the first function. And then for dx d theta, so first times the derivative of the second, plus second function times the derivative of the first function. Now you'll see in the on the next slide. Cosine theta times f prime of theta minus sine theta times f prime of theta. Okay, so the formal definition, now for looking for dy dx, we would take the derivative with respect to theta and divide it by the derivative of x with respect to theta. All right, so the slope of the tangent line to any polar curve at a given point is given as, so just putting them together. Now, this is just the chain rule, or excuse me, the product rule. So you don't have to worry about memorizing this. What you need to know is first, you have to parametrically define the polar function. Then we apply the product rule to each of those individual functions for x and y. And of course, provided that dx d theta is not 0 at some given point r theta. All right, so we're just going to do one example here. Find the points of horizontal and vertical tangency, if any, that exist on the curve of r equals 1 minus sine theta. So, looking at any derivative, we know horizontal tangent lines exist when the numerator is 0. Vertical tangent lines exist when the denominator is equal to 0. So let's first find dy d theta and dx d theta. So using our rectangular conversion, x equals r cosine theta. Now here r, that's just our function here, 1 minus sine theta times cosine theta. Y equals r sine theta, so then our parametric equation for y, 1 minus sine theta times sine theta. So now here, when we go to find the derivative with respect to theta, you can do whatever you want. If you want to distribute the cosine and derive that way, it would still need the product rule for sine theta times cosine theta. You can keep it as a product and apply the product rule. And this is what I mean by you don't have to memorize what the derivative function is, because it's just a simple application of the product rule. First times the derivative of the second, plus second function times the derivative of the first function. And that'll take some cleaning up here. So I am going to distribute in the negative sign. So negative sine theta plus sine squared theta minus cosine squared theta. Okay, sine squared theta minus cosine squared theta. It's not one of our known identities. Okay, so cosine 2 theta is cosine squared theta minus sine squared theta. And then we know our Pythagorean identity, we have to be adding them, and we could replace them with 1. So looking at this function, we have to solve for when this derivative is equal to 0. So in order to do that, let's get the derivative in terms of one of the trig functions. So I am going to use the Pythagorean identity, and since I just have sine theta here, I'm going to try to eliminate cosine squared theta. So negative sine theta plus sine squared theta minus, so the Pythagorean identity gives us cosine squared theta is equal to 1 minus sine squared theta. Okay. Distributing my negative, minus 1 plus sine squared theta, and then combining like terms, and I'm going to write it 2 sine squared theta minus sine theta minus 1. Okay, we'll come back to that. Now let's find dy d theta. So first times the derivative of the second function plus second function times the derivative of the first function. Okay. Cosine theta minus sine theta cosine theta minus sine theta cosine theta again. So combining these, cosine theta minus 2 sine theta cosine theta. Now for this one, I'm going to have to set this derivative equal to 0 as well, but I don't need to eliminate anything because if I factor a cosine out of both terms. Now if we think about setting this function equal to 0, I am able to set each factor equal to 0. All right, so I'm going to put these together just to sort of separate them again, but just so you can see, because in class you'll be working on problems that ask for the derivative. So dy dx is equal to cosine theta times 1 minus 2 sine theta over 2 sine squared theta minus sine theta minus 1. Okay, so horizontal tangent lines, set the numerator to 0. So I have where the cosine theta equals 0 and where 1 minus 2 sine theta equals 0. So we'll look one rotation around the unit circle. Theta is equal to pi over 2, 3 pi over 2. Subtracting 1, dividing by negative 2. I would get sine theta is a half. So first and second quadrants, pi over 6 and 5 pi over 6. I'm going to solve for this first for a reason. So vertical tangent line. Now look at dx d theta. 2 sine squared theta minus sine theta minus 1. When I set that equal to 0, you should recognize this as a quadratic trinomial, and we can factor that. So I have 2 sine theta times sine theta, and then minus 1 plus 1. Then that would give me positive sine minus 2, and it would give me the correct middle term. So I have sine theta equals 1. Sine theta equals negative 1/2. So theta is pi over 2. And now I have my third and fourth quadrant with the same reference angle, 7 pi over 6 and 11 pi over 6. Okay, so the reason that I had you find all the values of theta first, look at what happens. We have an overlapping value for theta. So if you think in terms of non-polar equations, what would that mean? If I put pi over 2 into my denominator, it would give me a value of 0. If I put pi over 2 into my numerator, it would give me a value of 0. So at pi over 2, the derivative does not exist. Okay, it's not going to be a discontinuity on the graph, but we'll talk about what the graph looks like tomorrow at pi over 2. So I have to eliminate that from my final answer. Okay, so I'm going to have 3 points where there's a horizontal tangent line on the graph. Now remember, coordinates are written r theta. So they're going to occur at 3 pi over 2. Pi over 6, and then 5 pi over 6. Now, where does the radius come from? Remember what our original function was. So the original function was 1 minus the sine of theta. And I'm going to have you do these. Vertical tangent line, there's going to be 2 points where there's a vertical tangent line. 7 pi over 6 and 11 pi over 6. Same function, so to find the radius, you're going to plug it back into the same original. So for homework, please find r for each point.